Hello everybody, welcome to section 1.2, Exponents and Radicals. We're going to go ahead and get started by talking about exponents. So let's let n be any non-negative integer. So n can be something like 0 or 1 or 2 or 3 all the way up. And let's let x be any real number. We say x to the nth power is equal to x times dot 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 times x n times. Right? So x to the n is just x times itself n times, right? So if we have, say, x squared, that's x times x, because the 2 means that x is multiplying itself twice, so there's 2 copies of x. If we have like x to the 1, that's just itself. The special case is if we have x to the 0, like what does it mean to multiply by itself 0 times? Well, we're just always going to say that that's going to be equal to 1. So no matter what number x is, if it's raised to the 0 power, it's equal to 1. Cool. So there's a few rules that exponents follow. So rules, let's see what they are. So the first one we have here is if we have x to the n times x to the m, so these are multiplied, and they have the same base, that's very key here, we can write this as x to the n plus m. All right. Kind of similarly, if we have x to the n divided by x to the m, so division this time, it's going to be x to the n minus m. All right. Cool. What about this? What if we have x to the n, and then that's raised again to the power m? That is x to the n times m, right? Cool. But what if we have different bases? What if we had something like, I don't know, x to the n times y to the n? So now they have different bases in the same exponent. Oops. We can kind of pull the exponent out. In a sense, we can write this as x times y to the nth power, right? Similarly, if we have x to the n divided by y to the n, we can do kind of the same thing. We can write this as x divided by y to the nth power. There's two more. They're a little funkier, but if we have x to the n divided by y to the m, so they're totally different, that's the same thing as y to the negative m divided by x to the negative n. And this will come in handy when we have something like a number to a negative power. So if we have like 9 to the negative 2, that's the same thing as flipping it over and writing 1 over 9 squared. Lastly, this is more of a radical rule, but if we have a fractional exponent, so x to the n divided by m, we're going to write that as the mth root of x to the nth power, which is the same thing as writing the mth root of x all to the nth power. Cool. So why don't we see these rules in action? So let's do some examples. So example, let's evaluate. Let's do something kind of simpler. Let's do 2 over negative 4. Let's do to the negative 2 power. So how do we evaluate this? Well, when I see this, the first thing I think of is, ooh, I don't like that negative power. So why don't we get rid of it? Let's do this. Let's flip it over, right, using this kind of rule right here. So this then becomes 2 times negative 4, and then negative 2 is just positive 2, and that's over 1. And then the over 1 doesn't change anything, so we can just write this again as 2 times negative 4 to the 2. And then let's expand out this part right here. So then let's write 2 times negative 4 times negative 4. 2 copies of negative 4. -4 times -4, that should be positive 16. Then 2 times 16 is 32. Good. Let's do one more example. Let's do evaluate. And then let's do 1/3 to the third power times 3 to the -1 plus 99 to the 0th power. So again, I think the first thing I'm going to take care of here is this negative power. And oops, what we're going to do is we're going to flip it over, right? So this can become 1/3 to the third power times, and this gets flipped over, so this becomes 1/3 to the 1 power, right? Oops. And plus 99 to the 0. Now we can use, because we have the same base, this rule here, and we can combine these two. So this becomes 1/3 to the 3 plus 1 is 4, plus 99 to the 0. Cool. This 99 to the 0 is really starting to bug me. So I'm going to go, yes, I remember. Even though it's 99, and that's a weird number, it's to the 0 power. And any number to the 0 power is just 1. So I'm going to write 1/3 4th plus 1. Cool. Now let's finish off this 1/3 to the 4th. We can do this move right here kind of backwards. So I'm going to take that 4th power and I'm going to put 1 to the 4th over 3 to the 4th plus 1. Now, 1 to the 4th is just 1 because 1 times 1 times 1 times 1 doesn't change anything, it's just 1. And then that's going to be over 3 to the 4th power. So it's 3 times 3 times 3 times 3. Well, that's 3 times 3 times 3 times 3, so that's 9 times 9, which is 81. So this becomes 1/81 plus 1, which is just 1 and 1/81. Cool. All right, let's switch gears a bit and let's start talking about radicals. Radicals. So let's say we have something like the nth root of x equals y. All this means, so this means that if we have y to the nth power, that's equal to x for n positive, oops, it's messy, positive integer, right? So radicals, kind of similar to exponents, follow some rules. So rules, and these rules kind of mirror radical rule, or exponent rules, sorry. So for example, this one probably looks familiar. If we have the nth root of x times y, that is equal to the nth root of x times the nth root of y. And this kind of follows the rule where if you have the nth power of x times y, that's the same thing as the nth power of x times the nth power of y. Be careful. So caution. The nth root of x plus y is not always equal to the nth root of x plus the nth root of y. Be careful, this only works for multiplication. Similarly, if we have the nth root of x divided by y, we can write that as the nth root of x divided by the nth root of y. Kind of similar to exponents. If we have nested radicals, so let's say we have the nth root of the nth root of x, that's the same thing as n times m radical x. Perfect. Okay, now these last two are going to be pretty important. So if we have the nth root of x to the n, that's just going to be x if n is odd, right? If n is even, this is what we have. We have the nth root of the x to the nth power is absolute value of x if n is even. Cool. So you got to pay attention to that. And make sure you keep track of whether your power is even or odd when you try to use these two rules. So let's see these in action. Let's do this. Let's simplify. Let's do the third root of 27 and then x to the fourth. Now this has a variable in it, but don't let that scare you. We're just going to treat it like a number. It follows the same rules as numbers do. So what I'm going to do is I'm going to use this rule first, because it's a nice rule, and I'm going to split up the 27 and the x. So I'm going to do the third root of 27 times the cube root of x to the fourth. If you note, 27 is 9 times 3, right? And then 9 here is just 3 times 3, and then times 3 again. So it's 3 to the third power. So we get this becomes this, right? So we can write cube root of 3 to the third times cube root of x to the fourth. And then following, 3 is an odd number. So we're going to use this rule here. And we can write 3 times cube root of x to the fourth. Cool. What about this ugly business here? Well, let's pull some trickery here. Let's do 3 times the cube root of x to the third times x, right, using that exponent rule. And then let's split it up again. Let's do 3 times the cube root of x to the third times cube root of x, right, using that radical rule. Now, again, 3 is an odd number, so what we get is we get 3, and by 3 an odd number, I mean this 3 here, right? So we get 3 times x, no absolute value bars, times the cubed root of x. Cool. So that's our final answer. Let's see that in action again. Let's do one more example. Let's do simplify. And then let's do root. No, let's not do 3. Let's do -3 instead. And then let's square it, and let's do x squared. And then let's do plus root 81. Cool. So how are we going to do this? Well, let's do the same thing. Let's go ahead and split this up here first. So then this becomes root -3 squared, and then times root x squared, and then plus, and then for this thing here, let's use that nested property. So secretly, every time you see a radical like that, there's 2's here, right? So then this becomes 2 times 2, 81. Cool. 2, in both these cases, is an even number, so we're going to get absolute value of -3 times absolute value of x plus, and then 2 times 2 is the fourth root of 81. Now 81, if you remember, is 9 times 9. And then 9 is 3 times 3, and then that's times 3 times 3. So it's 3 to the fourth. So 81 is 3 to the fourth power, which means that we can write this as absolute value of -3 times absolute value of x plus the fourth root of 3 to the fourth. Or even, so we write this as thus. We have absolute value of -3 times absolute value of x plus absolute value of 3. Cool. -3 in the absolute values, so making it a positive number, is just 3 times x in absolute values plus, and then 3 here is already a positive number, so that's just plus 3. And that's our answer. Cool. So now let's talk about fractional exponents. So fractional exponents. And we discussed these a little bit earlier, we touched on them, but I want to go over them in particular because they can be a little tricky, or at least a little scary. So let's say we have x to the m over n power. And as we saw before, this becomes the nth root of x to the m, which is just the same thing as the nth root of x all to the m power. So if we just stick to this rule here, we will be okay. So for example, if we do 4 to the 3/2 power, how do we figure out how to evaluate that? Well, we're going to follow the rule, right? We're going to do square root of 4 to the 3rd, which I'll just write as square root of 4 to the 3rd, like that. I'm going to split this 4 to the 3rd power up a bit. I'm going to write square root of 4 squared times 4, which then I can split up again using our radical rules as square root of 4 squared times square root of 4. Cool. So 2 right here is even, which means that we can write this as, because secretly there is a secret 2 here, right? We can write this as absolute value of 4 times square root of 4. If you remember, 4 is 2 times 2, which is 2 squared. So we can write this as absolute value of 4 times square root of 2 squared. And then, again, we have 2 is even, and the secret 2 there. So then this becomes absolute value of 4 times absolute value of 2. 4 and 2 are both positive, so this becomes 4 times 2, and that's 8. Cool. Let's see if we can do a more complicated example. Let's do x to the 3/2 times x squared all over x to the 5/2. Now, usually I don't like negative powers, but in this case, I'm going to take this guy and I'm going to move him up here. Oops, that's not a very good arrow. I'm going to move him up there. And we'll see why in a minute. So I'm going to take x 3/2 times x squared times x to the negative 5/2 all over 1. And the over 1 doesn't matter, so I can just write this as x to the 3/2 times x squared times x to the negative 5/2. Now, if you remember our exponent rules, we can sort of do this. We can do x to 3/2 plus 2 minus 5/2. And that is because they are all the same base, right? It's all just x. And if we do that math, we get x to the 1, and if you remember, that's just x. So using exponent and fractional power rules, we can take this nasty looking thing here and just get something much simpler. Cool. The last thing I want to talk about today is rationalizing the denominator, which most of you should have seen. Rationalizing the denominator. But I just want to review it so we make sure we're all on the same page. So rationalizing the denominator is the process by which we take something that looks something maybe like this, where we have like the nth root of x on the bottom, and we want to move this up here in a way so that the bottom doesn't have any roots in it. So the way we do that is we're going to multiply this by a fancy 1, right? So we're going to do the nth root of x to the n minus 1 power on the top and the bottom. And the reason we're going to do that is because then we can write n x to the n minus 1 over n to the x times n to the x n minus 1. This becomes nth root of x to the n minus 1 all over n, the x to the n. And then this becomes, depending on whether n is even or odd, let's say it's even for now. Or sorry, let's say it's odd. We'll just get this over x, which is perfect. That's exactly what we wanted. Good. Because now we don't have a root in the bottom. In practice, this will usually look something like this. If we say we wanted to do 1 over root 2, we wanted to rationalize that denominator, what we do is we would multiply it by root 2 over root 2. This would become root 2 and then root 2 squared. And that would become root 2 times the value 2, which is root 2 over 2. Cool. So if you follow these steps, you can rationalize the denominator.